is that the system has to, the qubit, it shouldn't undergo decoherence. So by decoherence of a qubit can occur if it mixes with some other states. It can be some environment state. So the purity of the qubit state deteriorates over time. So as long as it's state coherent and you can do gate operation on it, it's, yes. Gate time. So as I showed earlier, that you can do a qubit operation, and the time you need, and each of these qubit operation are different gates. For example, this is a Hadamard gate, a P gate, and another Hadamard gate. So they need some time. These are the gate times. So as long as your qubit state is pure and it's not mixed with your environment state, then you can keep on doing gate operation. So this the time during which this qubit should be should remain pure has to be long enough that you are able to do many gate operations. Then you should be able to define a universal set of quantum gates which you can combine to make any quantum any computation operation which is needed. So and then once you do operation, you should be able to read out what is the output of your computation. ठीक है, एक दफा you do a qubit, you should be able to read out the final state क्या है उसकी. And so these are the few requirements. Later on, a few other requirements were added. For example, qubit system should be scalable. ठीक है, it's not enough that you demonstrate just one qubit. It should be integratable into a large computational circuit so that you can integrate it into a larger system. And second, it should be integrable with a network so that you can add it to a quantum network, quantum internet, for example. So these are the extra physical bounds which came into the play later on after this Vincenzo's criteria. So the question then comes it, okay, we need to define a two-level system which is pretty quantum. What kind of an object immediately come to your mind? कौन सा object quantum होएगा? A photon, okay, apart from photon, but photon is something which is a flying qubit. Today, I would consider it only a stationary qubit. So what kind of a quantum system would you immediately? An atom, yeah. So a neutral atom is something which immediately comes to mind. Why can't I use a neutral atom? So the question would then be, how would you isolate a neutral atom? Okay, so can you plug a neutral atom from the environment, from the air or something like that? And how would you able to trap a single atom to be able to do computation on it? So that's the biggest problem which immediately which was being addressed by scientists in the 60s, not for quantum computational purposes, but for the purpose of doing spectroscopy, highly accurate spectroscopy on single atom. And for that, they wanted to isolate a single atom. And once you do that, you can also do quantum operation on that. So the idea in those times was to do spectroscopy in it. But the idea now is, can we isolate a neutral atom and do quantum operation on that? So, and the pursuit of this thing to isolate or to separate single atom led to several revolutions in itself. For example, the biggest technology which it developed was the cooling of atoms. So particularly laser cooling technology. So the idea for this was the following. Let's say you have a gas, which is, so you take atoms, you plug atoms from either from an atomic source or from air. It would always possess some thermal energy because of thermal kinetic energy. So the first thing you need to do is to cool it down. And by cooling it down, I mean to reduce its thermal energy, the thermal kinetic energy. So that's the laser cooling. So the laser cooling was a technique which was developed to cool down atoms. So if you take a very dilute gas of atom, you should be able to cool it down. And the idea was the following, that let's say if you have a photon which is incident from this side and an atom which is coming from this side, the photon, it does carry certain momentum. As the photon is absorbed by this atom, this atom gets a kick in the opposite direction, it slows down. So this was the idea for this laser cooling. And then you can think that, okay, you have a dilute gas of atoms, and then you can have laser from all sides so that you can cool down this very dilute gas into very slowly moving atom. And once they're very highly slowed down, then you can do quantum operation on that. So this was the idea of laser cooling. And then there were other cooling techniques which are called as Zeeman cooling or Zeeman slower, in which an atom which goes out from a source, it can be slowed down by passing it through a magnetic field. This is a solenoid, which is a variable solenoid in the sense that there is a magnetic field which changes along the z direction in which the atoms moves, and because of that, the Zeeman splitting in the atom moves. And there is a so I won't go into the details of this method, but this is another method to cool down or to slow down atoms. And this slowing down of atom, it led to a Nobel Prize in 1907 for these guys. So this was a Nobel Prize winning technology which was developed as a result of this efforts to do such things. Then, okay, once you are able to cool down, can you make a neutral atom qubit with neutral atoms? And it was first demonstrated by Harouche in 1996 and his group. So the idea was the following: you have a source which creates some atom, then you can cool down this atom to a specific low velocity, and as it passes through a cavity, such that the cavity is resonant with an atomic transition, then something strange can happen. For example, if your atom is prepared here in the excited state, and there is a single photon in the cavity which is running around, let's say this photon, as it is, this atom which is in the excited state, as it enters the cavity, and then because it's resonant, the cavity is resonant with the atomic transition, this atom can de-excite from its excited state to a ground state, emitting another photon. So you would have a second photon in the cavity after it emits a photon. And these photons can bounce back and forth. So this atom, if this atom is moving slowly through this cavity, this atom can absorb a photon again, getting back into the excited state. So what it does, as long as this atom is inside the cavity, it switches back and forth between the excited state, ground state, and so on. So what if you can control the speed of this, these atoms which are going through this cavity? So if the speed is very fast, nothing would happen to it, or maybe it just immediately emit a photon and is not able to recover to an excited state. Yes, so it would pass after the cavity being in the ground state, because as it enters the cavity, it emits a photon and it immediately left off being in the ground state. And let's say if you slow down the velocity, what would happen? It emit a photon, but it has enough time to absorb a photon again going into the excited state, and it would come out in the excited state from this atom. So you can prepare either the state in the ground state or the excited state. So this was another method which was shown. They changed the speeds here, and they can show that the atom ended, which came out of this cavity, was either in the excited state or the ground state, excited state, ground state. So they could control the qubits. Yes. So the details are a bit. So what you have is a source here. Then here you control the velocity of this. We already showed that you can slow it down. And then these are neutral atoms. And there's neutral atom, which, and here what they do is they shine UV light on the atom, so the atom goes into the excited state. So it gets prepared in the excited state. And once it gets prepared in the excited state, it moves through this cavity. And the cavity is resonant with the atomic transition. Okay, because cavity, you can make its resonance change by just changing the length of the cavity. Yeah, so that's basically the detail. So this was the first demonstration of a qubit preparation using neutral atoms, and it led to another Nobel Prize in 2012. So no, okay, but you might say, okay, this is not very helpful because you have a qubit, but this qubit is moving. I can't do much with it once I prepare it. So why not I can have, instead of a neutral atom, why can't I use an ion? Because ion, I can apply electromagnetic field to it and trap it into certain electromagnetic confinement. And this was exactly while this neutral atom technology was being developed, this was the second technology which was developed in parallel. And that technology was that of trapped ions. So the idea was the following, that let's say if you have some atoms which you can ionize, and once you ionize them, you let it pass through a certain trap, which is a quadruple-like trap. So you have 4 electrodes and these 2 electrodes at the other ends, and you give it some RF frequency. So what happens here to the ion, as the ions enter here, they experience a confinement potential because of that, and they remain trapped inside. And on top of that, you can use laser cooling to trap it even further or to slow it even further. And this, and then you can, so this is a real picture of atoms which were trapped inside, and their emissions were really, we are able to see the emission from each individual atoms here. So this is the ion trap technology, which was developed simultaneously. So the 1995, they demonstrated the first quantum logic gates with these atoms, and it led a Nobel Prize for Wineland. So now the question you might ask is, okay, whether you take an atom or whether you take an ion, the energy structure is quite complex. How do I make sure that I only, it is treated as a qubit? Because qubit should have only 2 energy levels and not many energy levels. So that is ensured. So for example, this is the energy structure, the energy levels of the ions which are used in the ion trap experiment. So what you do is, you choose your laser such that the laser is resonant with a certain transition, and this, the condition of energy conservation excludes all the other energy levels. So you can really choose your qubit out of a bunch of many energy levels which are within an atom or within an ion. So this gives you the selectivity to choose a spin, to choose the 2 energies, which is the energy of the laser. So imagine you would need some lasers to, you will need a trap to trap the atoms. Then you need laser on top of it to further cool it down. And then you need another laser to prepare these spin qubits or to read out these spin qubits. This is something. So, so these two were like the pioneer technologies in qubit preparation, but there are certain problems with this technology. And the foremost is that it requires so many lasers and alignment of so many lasers that practically, if you look at the system, it is very bulky. So this is one of the ion trap quantum computer, which consists of a few qubits, but the optics is so heavy and the optics is so involved that such kind of systems become physically unattractive from technological applications. So what you need is something of this sort. So you need qubit, which you can put on a circuit or integrated circuit, which you can integrate with all the other qubits within a circuit environment, and not something for which you have to isolate atoms and create all this. So of course, for that you need very high vacuum. On top of that, you need all these different lasers, not only cooling it, but also preparing the qubit and doing all sort of gate operations on it. So that's makes, so this is why the solid state qubits are important. That can you make qubits in a small piece of solid? That would be much more practical than these atomic gases, because for that you have to have very, very special conditions. And especially it's even better if you can make them out of semiconductors, because once you have them out of semiconductor, you can use the whole semiconductor technology, which we are so good at, to basically scale it up to whatever scale you want it to do. So this is the idea behind the solid state qubits, and particularly for semiconductor qubits. And that's why it's important to look for qubits in systems which are solid state system and not which are atomic systems. So now the question comes in solid. Okay, I want to go to solids. So what can I use there as a qubit system? And the natural thing which comes to mind is, what about electrons in a solid? What if you can somehow isolate or locate a single electron in a solid, and then use the spin of that electron to define your qubit? So that's kind of a natural idea which comes to mind. So let's see how does this works out. So imagine you have a band structure, or a semiconductor, so to say, with a filled valence band and an empty conduction band and some band gap, which defines it as a. So what if we shine light on this material, such that the frequency of the light is higher than the energy gap? You naturally create an electron hole pair. Can I play with these electrons now? Or can I play with these holes now? Because both of them are spin half particles. One is a spin 3 half particle, the other is spin half particle. And the answer is no, you can't. Because the moment you create these electron hole pair, they attract each other and they formed something which is called an exciton. And this particle, which is called an exciton, recombine within a nanosecond and emit a photon again. So this can't be used. You need something which stays there for a long time. So then naturally it comes to mind, okay, what if I dope the semiconductor with some electron, with some donor atom, so that you have some states, some impurity states near the conduction band. And then maybe if the impurity is very small enough, you have some chance that one of the electrons at thermal energy goes up into the conduction band, and you can play with this single electron in the conduction band. What about such a scheme? And the answer is no, you can't use it, because this electron occupy one of the states in the band. And those of you who have done condensed matter physics, they would know that this state is a block-like electron which has this form. So the wave function of an electron which is in a band has this this part which is the traveling wave. This is a wave part, and this part which is uh, a periodic potential part. And if you take the square of this wave function, you basically get a periodic function again, because the phase just cancels out, which means that the band electrons are not at a certain location, but rather they are delocalized over the whole solid. So if something which is delocalized, whose wave function is delocalized over the whole solid, you can't use it as a qubit. You want something which you can point to, or which you can know where it is. So this scheme also fails down. Then, okay, what if I don't do this? I don't go into the band. Okay, I don't want to play with bands anymore, because any band I go into, I would encounter this problem. Uh, what if I just stay with this impurity state and use these electrons in the impurity state? So what's the difference between the wave function of these impurity state and the wave function of electron in the band is that these impurity states, the wave function of those impurity states, it is localized to that impurity, and it doesn't belong to the whole solid. But the wave function of the electrons which are in the band, it belongs to the whole solid and just delocalized. So this might be a good choice here. But what you need is a bit better than this, and that would be you need impurities which are isolated. You don't impurities which are nearby, because one impurity can then interact with another impurity, and you would have something. You can't isolate a single qubit, so you need something of an impurity state in a solid which is isolated from all the other impurities, and in a perfectly clean crystal. Of course, you want a clean crystal, and you don't want too many defects inside the crystal. Otherwise, you have too many impurity states in there, and that's something which you don't want. So this, and the other thing which you want is that this impurity state is deep inside the band gap. By deep, I mean that it shouldn't be very close to the conduction band, so that at lower, even if it is close to the conduction band, what would happen? It would get excited into the conduction band, and it become delocalized again. It's something which you don't want. Yep.
How do you control where the impurity state is? Will it
Yeah, that's a very good question. First thing you do is you make a solid which is as perfect as possible, so that there is no impurity at all. And then you do is you intentionally dope it with an impurity of your choice, such that the energy level of those impurity lies somewhere deep inside the band gap. So you can choose the atom with which you dope your material. Yeah.
Sir, I have a question.
Yep.
So, what if we take the configuration of these impurity states in the form of ferromagnetic case? Because in that sense, in that case, the coupling strength will be minimum, so that even if the particles are very near to each other, but still they will be not be interacting with each other properly.
That's so. In that case, if you so you are what you are talking about is a collection of many spins which are aligned with respect to each other. The problem with that is you can't isolate a single spin, because each spin is entangled with a lot of many other spins.
But in ferromagnetic case, entanglement is very much is up to minimum, is of no use.
Yeah, okay, you can say that. That no, it is, but still there are fluctuations which you can't avoid. So even
Yeah.
if you take a ferromagnetic state, there are magnons which are sitting on a ferromagnetic state
Yeah, fine.
at some, and that would tinker with your spin qubit, no matter how carefully you prepare it. So this is what we have. So how do we achieve it? And the answer is okay. You take a perfect crystal, for example, a diamond. So what should be the color of a perfect crystal of diamond? What should be the color? It should be very, very shiny. It should be completely transparent. No color at all. It just look like glass. Okay. So If you want to buy a very good diamond, it has to be impure. Because the reason is that the diamond has a very large band gap. It's a very large band gap. It doesn't absorb visible light. Visible light just pass through it. Now, if you, let's say, if you take a very clean crystal of diamond and you replace a diamond atom with a nitrogen atom. So with a carbon atom with a nitrogen atom would have 5 electrons, so 1 extra electron than carbon. So when you do such a substitution, normally it's very common in carbon, in this diamond crystal, is that you also create a vacancy as well. You not only do a substitution of carbon with nitrogen, you also create a vacancy. So this kind of a configuration is called as a nitrogen vacancy centers in diamond, and this can be very well isolated. It's a very controlled doping mechanism which you can do here. So what happens in this case is you would have an extra electron here, and an electron from the nearby crystal can drop into this vacancy, because this vacancy is a lower potential region for it. So you have 2 electrons here, and those 2 electrons states can then, because those are impurity state, they lie somewhere deep inside the band gap. But more importantly, the combined two electron, they make a single, a triplet, a spin triplet state, a combined triplet state with total spin quantum number s equals to 1, so that it can have 3 different projection, plus 1, minus 1, and 0. And if you look at the, let's say this is a, if you look at in detail at this energy structure of this defect, it looks something like this. The ground state which of the triplet is split into an ms equals to plus minus 1 state and ms equals to 0 state. Why this is so is because of the environment in the crystal is such that the ms equals to 0 state is non-degenerate with the ms equals to plus minus 1 projection. So what you can do now is apply a magnetic field to it. What would happen to this degeneracy between plus minus 1 is one of the state would go up in energy, other state would go down in energy, and then what you can do is you can use this one of these either plus 1 or minus 1 depending on the direction of the magnetic field as one of the excited state of your qubit, and ms equals to 0 as the ground state of your qubit. So this is one possible qubit system which can be. Now what you can do is the following. So apologies for those who are online. So let's say this is ms equals to plus minus 1, ठीक है, और यहाँ ms equals to 0, ठीक है. जब आप magnetic field apply करते हो, doesn't have, nothing happens here, but this one it splits into 2 depending on कि आपके पास g v, जितने आपके पास field strength होगी इतना ही ये आपके पास क्या होएगा. This would be ms equals to minus 1 state, this equals to ms equals to plus 1 state, and then you can use this as your qubit system. वो separation आ जाएगी उधर, ठीक है. If you have radiation which is resonant with that, you can play with this qubit, or you can control this qubit. So this is one qubit system which is very much in research, and that's something people are really working quite a lot on. The other one is which has quite getting quite traction in the last couple of years, is that of phosphorus in silicon. So silicon is again a semiconductor, but if you replace one of the silicon with phosphorus, which has an extra electron, that extra electron carries a certain spin of its own. Not only that, it also carries a certain small nuclear spin, because silicon doesn't have a nuclear spin, but phosphorus does have. But that spin is very much smaller as compared to the spin of that extra electron which you put in, and then you can use this as your qubit. So an isolated phosphorus atom in silicon, it also acts as a spin qubit, because you can take the spin of this electron and apply a magnetic field to it, and you would have the spin up and down state energetically separated from each other, and that's your qubit defined there. What's good about silicon is, of course, we know how to fabricate very, very pure crystal of silicon, and we know how to do processing on this, because the silicon, all our technology is based on silicon. So recently, what they have been able to do is they have been able to create such spin qubit in silicon and make them entangled with each other. Yep. I mean, for complex computation operation, you need controlled correlation between spins, and that's one of the gate controls. So, for a single qubit, of course, we need to isolate them. But for more complex operation, we also need to entangle them. But in a controlled way, not it's something which we can't control. So here you can control it. You can control individual spin and then make them interact with each other. So this is something which is a controlled interaction, not something which is uncontrolled. So yeah, so you can look it up in these literature. So I have put up these references if you want to further read on it. And just basically last month, they this kind of a qubit, they reported a major breakthrough that it has reached 99% accuracy in terms of qubit operations. So, but now I come to what my work was about, and that is spin qubit, not of this sort, but of a different kind, and which is that in quantum spin qubit in quantum confined structure. So what do I mean by that? So this is a problem which is a undergraduate course problem, which should normally be given either in a statistical mechanics or condensed matter. Okay, we give you an electron gas, and we tell you that, okay, if you consider an electron gas and take Fermi-Dirac distribution, calculate the density of state of electron gas. So you can do it for the case in which you take a three-dimensional electron gas, or you can do it for a two-dimensional electron gas, or you can do it for a one-dimensional electron gas, or you can't do it for a zero-dimensional electron gas, but that's kind of trivial. I would come to that. So once you solve this problem, what you find out is the density of state function. It is a square root function in energy for this three-dimensional. So this is a continuous function in energy, which means कि आपके पास जो bands के अंदर energy density है, it's a continuous function of energy. That's why bands have continuous energies within them. ठीक है? You don't have discrete energy levels in there. But as you so that's why if you plot this energy density for, let's say, conduction band, it's a continuous function. Similarly, for the valence band, it's a continuous function. So within the bands, if you have a three-dimensional solid, the density of state function is a continuous function with no jumps in it. But as you try to reduce the dimensionality of this electron gas, what happens is that you start creating some singularities in your density of state function. For example, for a two-dimensional electron gas, you do have these step-like function of electron density state. You further reduce it, you start getting these kind of a density of state function. So you are adding discreteness into your band structure. And once you are completely confined it in all three different directions, what it leads to a density of state function, which is completely just like delta-like functions. So what does it? Yes.
Yeah. So does this jump that you are showing us, like in quantum wire and quantum wire, has to do with quantum phase transition? And so
no, you can't call it quantum phase transition. It's just the quantum confinement effect become more dominant than the tight binding phenomenon which occurs in a band.
Fine.
So for example, if you imagine the band is given rise by the tunneling between neighboring atom. Let's say if I take the tight binding approximation, in this case, I'm assuming that, okay, that thing is there, but on top of that, you have a quantum confinement effect, which is basically a particle in a potential well.
Okay, so this is confinement phenomenon, right?
Yeah. So the confinement. So what it means is the confinement gets stronger and stronger as you make the dimension smaller and smaller. So when the questions come is, would a sheet of paper show such a density of state, for example? Why?
Like 2D Dirac materials?
No, it's not. I mean, for a piece of paper, the thickness is still very large. It's not small enough. So you need to work on a scale or Woolen scale. You have a de Broglie wavelength of electron within a solid. So you take electrons which are moving, which are near the Fermi energy, and you find out their de Broglie wavelength, and those de Broglie wavelength, and most of the solids in the range of 20 to 70 nanometers. It means that this discreteness start appearing when the dimensions of the solid are become smaller than these de Broglie wavelengths. Okay? Not for a piece of paper. It won't work for a piece of paper, but it works for very thin electronic gas, which is of the dimensions either this or smaller than that. Okay? So these discreteness pairs become apparent, so what one can say is that the quantum confinement effect dominates the band structure here, or the electronic structure. So it's kind of going opposite to when you mix bands in a solid. So you start with isolated atoms which have very discrete energy levels. You bring them closer, you make a solid out of them, and what do you have in a solid is bands of energies and not discrete energies. You are going the other way around. You are making the solid small again, so that you have discrete energy levels start appearing again. So how do you make such a structure? So this structure, which is confined in all three directions, it is either a quantum point or it's called as a quantum dot. This is also called as an artificial atom for the obvious reason that the energy levels are just like discrete energy levels of an atom. So how do you make them? And one of the technique is the following, that you take one material, for example, indium gallium phosphide, and then you deposit very thin layer of another material, which is indium arsenide, so that this indium arsenide has slightly larger lattice constant than the lower material, and you start depositing it. Okay, so upper वाली material को क्या होएगा? It becomes slightly stretched, क्योंकि नीचे material का band क्या कहते हैं, lattice count small है, ऊपर का ज़्यादा है, so the other one gets stretched, and when it gets stretched, you deposit more and more material. It releases that stress by making small islands like this. Okay, you make those small islands, and then you cover those small islands by this lower material again to have a symmetric confinement on either side. So what you have now is an island of one material inside other material. Dono side पे it has other material. So what you can do is, so once you this kind of growth method is called as Stransky-Kruston of growth, and as a result of this, you have these small islands appeared randomly at different places. They appear because those atoms want to minimize their energy, and they minimize their energy by making these small islands. Now, if you choose your material carefully in such a way that this outer material has a larger band gap, जिसको मैं barrier material कहूँगा. If this has a larger band gap and this material जो small island है इसका जो material है, it is a smaller band gap, so you have an energy bandscape which looks something like this. If you are outside here, you have a larger band gap. You are outside here, a larger band gap. Inside, you have a smaller band gap. So what you have done is you have created small islands. So if an electron, which is here in this conduction band, if it goes here into this island, it will get trapped there and can't come out. So all the particles which are in this small island, they get trapped there. And if you solve for the electronic structure of those electrons which are trapped inside, they are discrete energy levels and not continuous bands anymore. Just because of the quantum confinement is so strong. So if the size of these islands are usually on the order of 20 to 30 nanometers, smaller than the de Broglie wavelength. Any question here? Okay, so this is how you make these artificial atoms using quantum confinement and not using impurity atoms. Okay, this is an approach. So you take this atom and then you can think of, okay, you cool this semiconductor down. Yes. Okay, that's a good question. So if you look at this structure, there's a bit of inhomogeneity there. And this is a long-standing problem in quantum dot system, how to make the system as homogeneous as possible. There has been some success on that, but it's still a researchable problem. So people are still working on making these dots as similar as possible. Yes, so yes, so there is this problem still with this system. Okay, so what if you cool down this system to, let's say, 4 Kelvin or 3 Kelvin? That's what people usually do, is because you have a semiconductor material, the whole, you have discrete energy levels inside the quantum dot in the valence band and discrete energy level inside the conduction band. So at low temperature, all those valence band states, discrete states in the valence band would be filled and the conduction band would be completely empty. Okay, makes sense? And then these states, they do also have, so these are like like shells in an atom, you can assign some orbital angular momentum to each of these shells. So just like an atom does. So what if I take this kind of a neutral of this kind of a system and shine light on this quantum dot? What I can do then is excite one of the electron here from the valence band into the conduction band. And if I do so, I create an electron in the conduction band and a hole in the valence band. But this time, though both of these electron and holes are confined inside the quantum dot and they can't move around there. So I have created something which is called as an exciton represented by, and because it's a neutral exciton, you have one positive charge, one negative charge. So it's a neutral exciton. It is represented by x0. So a zero ground state is just this crystal system. An excited state would be this excited state, which is the excitonic state. But again, this exciton would recombine, emit a photon. You can't use this electron anymore. So you get the same problem with this as well. But what if I do something different? And what I do is somehow, if I'm able to tunnel an extra electron into the quantum dot conduction band, let's say I have this situation as my ground state, in which this electron has an extra this quantum dot has an extra electron in it. Okay? And that electron is somewhere there. Now this is a charged electron with an extra electron in it. And what if I shine light on it? So this would be the ground state of this single electron state, which is here. If I shine light on it, I create an extra electron here and a hole there. So you would have two electrons and a hole there. This species is called as a charge exciton and nota. Of course, this charge exciton recombines as well. But that's another issue which I would come to. So I hope you get the point. Yes.
How do we electron? How do we pump that into the
How do you do that? Yeah, that's the whole problem I'm coming to, because that's basically the crux of how do you define qubit in here. ठीक है, उसकी तरफ आता हूँ मैं. ठीक है, so you can look it up, and then you can also think about putting an extra one more electron into the system, and you would create a doubly charged exciton here, and so on and so forth. Now the question which you are asking is, how can I control the electrons inside a quantum dot? And that's something which I come to now. So imagine I make a diode, and a diode in such a way that you have quantum dot layer here. So if you look at this is the layer which contains my quantum dots. So they are there. And this quantum dot layer is then on either side is has some barrier layers on either side. And you have this layer here, which you doped with a very high density of electron. Okay, so you have a very highly dense electron layer, जहाँ पे electrons काफी ज़्यादा available हैं. Then you have a neutral area, जहाँ पे electrons there are no electrons here, and then you have quantum dots here. So if you, and then you can make a diode out of it. You can have metal contact here, and you have contact here, and you can apply a potential to this material. So what happens to a solid when you apply an electric field to a solid? The band, they start bending when you apply an electric field to a solid. So imagine what would be the band gap here inside a quantum dot. It would be something like this. Yes. And then you have, at a certain distance from this quantum dot, you have here a layer which has a high number of electrons available to it. Okay. Now the question is, there's a tunneling barrier between this layer and the quantum dot. So these electrons which are here have to tunnel into the quantum dot so that the electron can get, so that the quantum dot can get charged by a single electron. How do you do that? You apply bias to this device. ठीक है, you apply bias to this device. जब potential apply करते हो, what happens is the bands start bending. The bands start bending. This potential barrier become narrower and narrower. And at a certain potential, you would have a higher probability of electron tunneling into the quantum dot, and you can charge the quantum dot deterministically by just applying the bias. Yep.
where does the potential value come from?
The potential barrier, it becomes, so what you do in these devices is some kind of a band engineering. ठीक है, you know कि यहाँ पे quantum dots है, एक quantum dot है जिसका band gap इस तरह है. Okay, and then what you do is यहाँ पे at a certain distance from the quantum dot you create you create a layer which you highly dope with electrons, so it has a high supply of electrons. Okay, so you have a layer at a certain distance from this quantum well which has a higher density of electrons, and then what you do, you want to tunnel electrons into this quantum dot device, and that's how you want to charge it with. So this is the wavelength. So this is an experimental result from one study. Unfortunately, you can't see very much nicely here, but this is wavelength, the emission wavelength, and this is the gate voltage which you apply to this device. So when in this voltage region, the emission is from neutral exciton. So the dot is neutral. There is no electron inside. And when there is no electron inside, if you shine light on this in this quantum dot, you create this electron hole pair, which recombine, emit a photon. And that's what you see here. This line represents those photons which are emitted as a result of the emission of this light. But when you increase your bias, what happens is that the bendings become stronger and stronger. And in this region, what happens is this is x raised to a power, this ground state appears. And because of this ground state, you have now immediately there's a change in the energy of the emission. And it's because you no longer have neutral exciton emission, but you now have an emission from a charge exciton. And that's how we find out that you have charged your quantum dot with a single charge, single electron. These are called a plateau structure. If you increase the bias still further, you create states which are doubly charged. So it's just by applying potential to this device, you can charge it, you can have a potential region in which you have no electron inside. Then you change the potential, you have one electron inside, you change the potential still further, you get another electron inside. Now the question to you is, why, if let's say in this case, if there's an electron which goes in there and I'm increasing the potential, but still it's not being charged by two electrons, it's still I have a single electron there. So why is that? You think about that. So why there is a threshold voltage जो आपको चाहिए उसको doubly charge करने के लिए? No, even more fundamental. You have a small island जिसके अंदर आपने extra electron डाला हुआ है, and you want to put an extra electron in there. Repulsion. So this is something which is called a Coulomb blockade.
Don't you just have the answer right there? Coulomb blockage?
लिखा हुआ है नजर नहीं आ रहा. Okay, ठीक है. It's just like put a solution over. Okay. So this is something which is called as a Coulomb blockade, and it's something which is very common in these small nanostructures. So you have a Coulomb blockade, and you need at least a certain threshold potential to get another electron get injected into this quantum dot. How much time I have? Okay, so I have quite a few slides left, but okay, I will try to be a bit fast. So now you know how to get a single electron inside. Now I come to this problem. You have a single electron here, which is your ground state. You can excite one electron hole pair, you get something of this configuration. Okay? So what about this extra electron which you have put inside? It can either have a spin up or it can either have a spin down. In the absence of a magnetic field, both of this spin would have the same energy. Okay? And similarly, the extra excited state which you get, which would have an electron pair and a hole, an electron pair and a hole, but this this state would have a different spin hole spin as compared to this state, because you have excited it from a different electronic ground electronic state. So these are the four different possibilities which you can have. These two states would be degenerate. These two states would be degenerate. What you have, if you apply an electric field, a magnetic field to this quantum dot, you would induce Zeeman splitting, and what you would do is you would induce the Zeeman splitting between these two states and these two states as well. Now you have a 4-level system now, not a 2-level system, but rather a 4-level system in which you can have 4 different transitions possible, these vertical transition and these cross transitions. Okay? So these are, so now let's talk about these a bit. you have this system जिसमें आपके पास 4 energy levels हैं, and you apply some magnetic field to it, and now you want to play with this. You can immediately tell that this would be your qubit system. Somehow this would be your qubit system, because this is something in which is just a qubit immediately. No, you can have the spin projection here for the electron and the holes. The electron have either a plus minus 1/2 spin, and the holes would have a plus minus 3/2 spin projections. Okay. Now, what about these vertical transitions? So this state has a spin plus 1/2. What about the spin, the total spin of this spin projection of this state, upper state? क्या होएगा? Plus 1/2 minus 1/2 cancel out. इसका क्या है? Plus 3/2 है. What would be the total spin? Plus 3/2. So plus 1/2 plus 3/2. What is the angular momental difference between these two states? Is plus 1 or plus h bar. Similarly, what is the energy difference between these two? This is minus 1/2. This is minus 3/2. This is equal to minus 1. Okay. So you need, for the vertical transition, the difference in the spin projection is either a plus 1 or a minus 1, and which means that this transition is something which is dipole allowed, because dipole transition, the dipole transition rule tells you that you can have transition which is plus minus 1 changed by the spin projection. But what about this cross transition? You go from a plus 1/2 to a minus 3/2. How many? What is the change in angular momentum in this case? 2. That's minus 2 here. And in the other vertical, you would have a plus 2 here. So, but this is dipole forbidden, because dipole doesn't allow, transition doesn't allow for that. So what does it mean? That the vertical transition are stronger, and these cross transitions are much weaker transitions. And one other thing which you need to take care of, these transitions, which are the vertical transition, has to obey conservation of angular momentum, which means that they can only be done by either a right circular polarized photon or a left circular polarized photon. So this transition can only be occur by a right circular polarization photon, and this can only occur by a left circular polarization photon, because both of them carry an angular momentum of plus h bar and minus h bar. Okay. So these transitions, the vertical transition, they are only possible using circularly polarized light of a specific rotation. And basically this defines your qubit. Now the question is, I do have a single spin here. How do I make sure that the spin either is initialized either in this state or in this state? Okay? I can trap one electrons inside, but वो electron इधर भी हो सकता है, इधर भी हो सकता है. How do I make sure that I deterministically initialize it in one of these? Riz, how much time I can take further? कितना time ले सकता हूँ? Hello?
Well, I mean, जब तक आपको नजर आ रहा है कि आपके सामने लोग सुन रहे हैं, तब तक आप बोल.
ठीक है, okay. It's okay. So let me come to that problem now. So let's say you have an electron here. So you start with a system in which the electron is in this state, okay? And you shine this sigma plus light on this system. क्या होगा? It would get excited. It would do a vertical transition. It would end up here. Okay? Now it can either go from here to here, or it can go from here to there. Okay? But this transition is much stronger than that transition. As we already established, cross transition is weaker. क्या होगा इसको? It would come back. Okay? It will get excited again, come back, and these kind of transition, they are called as cyclic transition. And this would only be true अगर ये transition rate, which is capital gamma, is much larger than small gamma. Okay? That would be the obvious thing which would happen. जो gamma, जो ये वाली cross transition है, this would be much less frequent. Okay? But imagine, let's say, this vertical transition occurred for, let's say, 10,000 times, and 10,001 time this cross transition occurred, because nevertheless it has some probability. Okay? And the electron end up there as a result of that. What would that electron do? So if either karega, let's say this transition is even weaker probability than the cross transition. Remember, the only laser which is shining on this system is a sigma plus laser of energy difference equals between these energy levels. ठीक है? आपके पास this is the only laser which is available here. ठीक है? यहाँ से यहाँ नहीं जा सकता. ठीक है? It gets trapped. It gets trapped here. And what you have done here is basically you have done something which is called a spin shelving. You have done something which is called a spin shelving. Okay? You have trapped your electron in a certain spin direction. So if you look at the wave function of this electron, it is a wave function. So one other important thing which I would like to mention here, that the quantum dot is not made of one atom, but rather made of from 10,000 to 50 or 60,000 atoms. Okay? So there is so if you take a quantum dot as a pyramid-like structure, the electron which is trapped here, it has a much larger wave function than the size of an atom. It has a wave function equal to the size of the quantum dot roughly. So you have a big wave function of an electron sitting in a quantum dot with a specific spin. So you have initialized your qubit in a specific state here by the spin shelving effect. Now you can play with this spin now. Now the question that someone asked was, okay, you might also ask that how do you make sure that you do this process is in just one quantum dot and not many different quantum dots? Because at the end we want to initialize only one qubit and not many different qubits. So the answer to that is you have many different quantum dots within the sample, but what you do is you make sure that the density of the dot is small, and then you focus your light on only one dot so that all this process occur only in a single dot and not in many different dots, so that you can have only single qubit prepared. Yes. ये पूरा quantum dot. So you have an electron which is trapped inside, and that electron has a very big wave function with a spin in its other electrons. Yes, but they are trapped at their atomic site, and they don't belong to the whole quantum dot. So they are localized electrons. This one is an electron which belongs to this wave function which belongs to the whole quantum dot. Yeah, it's special because it came from outside. It tunneled into the system from outside, and it is a quantum. It's a wave function which belongs to the whole quantum dot. So it's a delocalized wave function which you can play with now. Now the question is, how stable is this spin? I mean, your question was, would it, अगर आपने यहाँ पे spin create किया है, wouldn't it go there as well? ठीक है, because it's a low energy. So there is, of course, there might be, this process is called a spin relaxation. So you have created spin in a certain state, but this spin can relax into another spin state, and this process is certainly possible here. But for an ideal system, what you want is that spin relaxation is much smaller than even this gamma. Okay? This small gamma, because you want this to stay as long as possible here, and this rate to be as small as possible. Okay? This rate is defined by relaxation time of the electron. कि कितने time बाद ये यहाँ से यहाँ तक relax कर जाता है. That's this time t. The larger this time is, the smaller is this transition rate. So this rate is defined by two main processes. One is, of course, we say that the electron tunnel from this layer into the quantum dot, but this electron can go back as well, can tunnel back. This is called the co-tunneling process. So this is the limiting thing here. Because during the co-tunneling, what happens is that your spin gets randomized. So जो नया spin आएगा, it would come with a different spin. So you can lose this spin state जो आपने prepare करी है. The other thing is, imagine you have an electron wave function which is sitting inside the quantum dot, but that quantum dot consists of thousands of atoms, and those atoms have nuclei, and nuclei also have magnetic moments. So this wave function of a specific spin is sitting in a sea of nuclear spins as well. And those nuclear spin can interact with the electron spin. So some of those who are taking this course on the selected topic, they have already seen Heisenberg exchange Hamiltonian. How do two spins interact with each other? So so the spin of the nucleus and the spin of the electron, in dono ka z component, plus you have an up of the nucleus spin and a down of the electron spin, and a down of the nuclear spin and the up of a projection on the electron spin. What this term does is it transfers the spin of the electrons into the nucleus, or the nucleus spin into an electron spin. So what would happen those, although you have defined this spin in a certain direction, these electrons, because those nuclear spin are randomly fluctuating even at 4 Kelvin, those random fluctuation can affect your spin qubit. So this is the limitation on this spin qubit system. What you can do is you can measure this spin relaxation time. Uh, so this is just the last couple of slides, which I would finish here. So you can measure this time for how long this spin remains stable inside the quantum dot, and you can do it by the following way. First, you apply, what you do is you apply a pulse, which is called as a pump pulse, and that pump pulse, it creates an electron here, okay, in this state. So what happens is you have a brief burst of the cyclic transition. Cyclic transition hoti hai, you get a lot of photons out, but the moment this electron is shelved, transitions slow down. There is no more emission anymore. Okay? So you have the dot become dark, no more emission, no more emission. And then what you do after a certain delay, you apply a pulse again to see whether you have whether kuch transition ho sakti hai ki nahi ho sakti. And if there is some small transition, it means that you do have some small rate of spin change. Agar bilkul transition nahi ho rahi hai, iska matlab hai your spin is still shelved into that state. Okay? So the height of this signal after in the probe, it tells you okay, how is your spin still shelved or not. And this is something which we measured, and we saw that the spin system, it's remained shelved up to a few milliseconds time. You can increase this time by changing the tunnel barrier, but the problem with that is that the fidelity or the probability with which you create this spin state, it drops down. So there is a certain compromise which you have to make, and there is some complicated physics here. But you can basically increase the spin relaxation time up to 0.3 second, and 0.3 second is a very, very long time, and you can do several hundred gate operations while doing that. But the problem with this is that the probability with which you create this spin state is almost 77%, not 100%. That's something which you would ideally want it to be 100%. Yes. Huh. Ground, it is in the ground state of a single electron. It's a ground state of a single electron in a quantum dot. कौन से वाले में जो spin up state है? No, you can't do it. You can in this scheme either आपको magnetic field पर उलटना पड़ेगा उसके लिए. That okay. You want to so उसके लिए फिर what you have to do is you have to apply an energy level, apply an electromagnetic field जो इन दो transition के बीच में resonant हो, and you apply a pi pulse such that all the population of this state go into that state.
Okay, so first you initialize this one and then apply
pulse to yeah. So it's just like like an operation of the block sphere in which you change all of the population. Yeah, you do a NOT gate. Yes. So yeah, so I think I will finish with this, but there are, as you can already see, there are problems with this qubit. We still can't reach 100% fidelity. When we try to reach there, then the times for which the spin qubit remains stable become shorter. If you try to increase that, the fidelity decreases. The next step would be, okay, you have created this. Is the question you are asking is, next what we would do, we know that we have these two spin states and we can create our population in this. What if you have, we have microwave pulses, which we can make incident on this quantum dot and make the population change from here to here. Is basically just like you are doing qubit operation on this spin qubit. That's the next step on the system. So all these results are published last year. So it's a combination. So a work which I started in 2014, and this paper, it combines the study of all the last rather half a decade of work. So just as a parting thought, we also were able to make a spin qubit out of all the nuclear spins as well. So what we did was, because we know that the electron can transfer its spin to the nuclei, if we repeatedly create our electron in the same spin state, what would happen that electron would eventually transfer its keep on transferring spin to the nuclei, and all the nuclear spin would align into the same direction. So that's something which we already showed, and we showed that that qubit stays for even longer time. It stays for a few seconds as well. Okay, so it's something I won't go into detail, but yeah. So what I showed you is how you realize qubit, what are the physical requirement, how is it done in solid state system, and particularly in system in which you have quantum confinement. Yeah. So with this, I would like to go to the acknowledgements. So all this work was done at the University of Sheffield, where I did my postdoc. So this project was initiated by Morris Skolnick and Evgeny Chekovich under we get a grant from EPSAC, the main funding agency in UK. And the samples were prepared in National Epitaxy Facility Lab by Edward Clark. Yeah, and with this, I would like to thank you as well. Yeah.
Great. Thank you very much, Ata, for this very lovely introduction to solid state qubits. You're going to have to handle, or you or someone else is going to have to handle the questions in the room. Let me do my bit and see if there's any questions from the online audience. So if there's questions, just unmute yourself and go ahead and ask it.
Yeah.
We're going to give you like 20 seconds to do so.
Yes. No, we don't yet.
Ata, can I suggest? I didn't want to interrupt you during the talk. It would be helpful if you could repeat the question, because we can't hear the question.
Yeah, I got the problem. Yeah. So the question is, can this is the work which I did at another university? Can we repeat it here? And the answer is no, not with the current facilities, because the samples, the dots which are prepared for this qubit system are highly specialized, or only a few groups in the world can prepare such. So they have worked for several decades on this quantum dot system to enable it to prepare such pure quantum dot samples, which can show very long coherence times. So first of all, this is extremely hard to make the sample. Second one is you need very low temperatures. The highest temperature you can go for the system is 4 Kelvin or 3 Kelvin. So you have to work at that temperature to work it out. The spectroscopy is not that difficult, but the problem is how do you get good structure? And then you also need some kind of pulse laser as well to show, because a lot of qubit operation is based on pulse laser. So yeah, we do have quite a lot of stuff missing still to be able to realize it. Yeah, the problem with liquid, so the question is, there was some implementation of the quantum dot qubit within a liquid. The problem with liquid-based quantum dot is they have very high coherence decoherence as compared to this system. So the main problem is, if you take a quantum dot in a liquid, the surface charges are constantly keep on changing because there is liquid surrounding it. So that is the limiting factor. Imagine you have a particle of 20 nanometer, okay? And because that particle has a surface, that surface is an imperfection in the crystal, because the crystal is a perfect solid, and the edge of the crystal is an imperfection. That nanoparticle size has imperfection on all its sides. So charges can get trapped into that imperfection. And imagine you have an electrons inside. Those electrons can feel the electric field of those trapped charges very strongly, and they keep on constantly changing. So the decoherence in that system is very large. Yeah, it's very difficult to. So that's why you embed these quantum dots into a very well-defined crystal so that it is very safe from external environment. Yep. Okay, that's a good question. So we are able to initialize the qubit system, but the initialization is not 100%. It's let's say 80% or close to 80%. So the first thing which needs to be done for this quantum dot based system is to increase its it to as close to 100% as possible. So that's the first thing. The second criteria, it does obey that it can be fairly isolated from all the other contributors. So that's something which can be done. The other thing it can be, you can also do operations on it. So that's something which needs to be done, but in principle it should be possible once when you can prepare it with. So that's the next step in this project would be to demonstrate the gate operation on these spin. The scalability, in case of scalability, is a very favorable system because you can create many quantum dots in a very small chip. So it's much scalable than the quantum system which are currently, let's say the Google quantum system is not that scalable as compared to this system. Yes. Yeah, that's what I was. So the question is, no, we have attained a qubit. How can we change the state? And the answer is, yeah, we know that the system has. Yeah. So this is the answer. That we know you have a spin down state and a spin up state. Of course, the energy is upside down, but nevertheless, it doesn't matter. What you can do is you can make a microwave which is incident, which is resonant with this transition between the spin up state onto the quantum dot, and you can induce this transition. So if you remember, if you can induce transitions of and change the population from completely from this state into this state by making a pulse of microwave of a specific width incident on it. Okay? You can choose your width and you can choose any operation on your qubit which can be performed on the spin state. So it's a matter of, so it's not that difficult a system. So you can choose, let's say you start with this system and you want to come back to this. What you have to do is you have to choose the duration of this microwave pulse, and it would change your population from this state completely back to this state. Just by decreasing the width of those pulses. Again, if you do a 1 millisecond pulse for complete transfer of population from one state to another, you have to do half a millisecond pulse for that to create a superposition. That would be a Hadamard gate. Yeah. Yep. Okay. Yeah. So any more questions? So if not the case, then yeah, I think I would close the, yeah.
All right, thank you very much. Thank you for listening. And just our usual advertisement, this is a weekly colloquium. Stay tuned. See you guys later. Bye-bye.